So single linked list is one directional. There was a problem when we saw this thing, that when you're going in one direction and you like to stop or you like to go back, okay, or you want to remember the one before, it's not possible to do that because the whole the linked list is unidirectional, single directional, just goes in one direction. So let's think about a situation where you would have to go back and forth, go forward, go backwards many, many times. Can you think of a situation where you're storing data and you have to go back and forth again and again and
Doctor,
again? Yes.
when we added stuff in the singlet linked list last week, we actually kind of did the previous, and then like the previous is what we do in double linked list, right? Because like that's how you go back.
Right, yes. But it kind of gives you the idea, yes. But we're going to see this thing today. Okay. So my question again, can anybody think of a data, a certain kind of a data which allows you to go back and forth?
Mm-hmm.
So think of it like this. Imagine I had some kind of a list. Okay, there's a head. And all the nodes are connected. Okay, let's say there's some data here. Actually, this is not sorted. Okay, let's say I would like to find 1. So always we start at head, we go and check, 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 we found it, so we're going to return this node. What if somebody would like to find 3? So in this case, we start at head, the first node is 3, so we return. But if somebody says, hey, I need to find how many 3s are there, I need to simply count how many 3s are there. So in this case, you start searching from here, check, okay, we found 1, go next, found no, next, no, next, we found 1. So you need to keep going all the way until the end, and then, okay, we're going to return, hey, we found 2, the nodes that contain 3, 2 nodes that contain 3. Okay, so again, my question is it possible that you go front and then you go back and front and back and front and back?
You can start in the middle and make one go next and one go previous.
Okay, good. So one thing is searching. Okay, when you're searching for certain information, if you're somewhere in the middle, okay, and you already know that everything on the left side is sorted in a certain way, everything on the right side is sorted in a certain way, then it will be easier for us to reduce the search time. Okay, reduce the search time, because if I start in the middle now and I know for sure, let's say, that what I'm looking for is not on the left side, this means I need to go on the right side. Okay, I'll go on the right side and search my information over here. So naturally, this is going to reduce the search time by at least half. Okay, here's another thought. Let's say we start searching from here. Okay, imagine this is already sorted. We already have 1, 2, 3. Okay, let's say this is 6. So I want to look for the largest element in the list. So one approach is to start at the head, keep searching, okay, until you reach the end, and then you realize, okay, 6 is the largest value. But to search this particular list, I had to check 6 different nodes. Imagine I could start from here. How long would it take to search 6?
Half the time. If we limit the operations to half the list size and put a cursor at the end and at the beginning and stop at the middle. Okay. Make one go previous and make one go next and stop at the middle.
Right. So imagine if this is 2-directional. Okay, I can go left and I can also go right. Okay, for every single node. We can go right, we can go left. So if I already know somehow that the larger values are on the right side of the list. So instead of starting from the left, we can start from the right. We can go this way, this direction. If I could do that, this means perhaps my search time is going to be improved. Let's say I'm searching for 5. Okay, I know that in the middle I've got 3 or 4. This means 5 must be on the right side. So instead of starting from here, why not start from this side? Okay, so I can reduce the search time. So that's a cool thing. Okay, search can become faster. Search can become faster if I can implement the 2-directional list. Okay, how about insert? Let's say I would like to insert something. Now, let me take you back to single linked list. When we were trying to insert something, we had 2 scenarios. Either we insert in the beginning, or we insert in the middle/end. Remember, we wrote a little bit of code which was a bit intelligent. That'll take care of both scenarios if you wanted to insert in the middle or at the end. So there's 2 situations. Either you insert in the beginning or insert somewhere in the middle or the end. Okay. Now, what if we would like to insert certain number of nodes, or let's say even 1 node, somewhere in the middle of the list? So remember, to insert something, we had to search if it was not by default in the beginning, which means you had to go over the list, find the appropriate position, and then go and insert the value in there. So if I have the 2-directional list like this one, okay, I may save time. Okay, so I can save time on insert. I can do the same thing. I can save time on remove when you're trying to remove something. So for remove, okay, this was important because we needed to remember the previous one and the following one. Okay, but now if this is 2-directional, you don't have to remember the previous or the next one. Okay, so let's look at this data structure. A double linked list is very similar to a single linked list. Only difference is now every node is going to store 2 pointers. So let's see how this works. We're going to have the node class. Okay, node class. Remember what methods did we put in there? So this is my node API.
Constructors.
An empty constructor and a constructor with a value.
Okay, very good. So we have a constructor and integer value. All right, what else?
And check if empty method.
No, for the node we don't need to do that.
For the node.
So we can have the integer x value. We had node next. Okay. Now what's new is we're going to define node previous. Okay. So there you go. That's your API. Again, we're not writing code here. That's the purpose of the API. We just mentioned the attributes and the methods for this class and their definitions. Okay. Now for the double linked list class, okay, it's going to be identical to singular or single linked list. So we're going to define the DLL object. Okay. Is it the object or the constructor?
The object.
Constructor. Okay. And obviously we're going to have the insert. Okay, so like before, we're going to pass it a value. Okay, and then we have the search method. Okay, obviously we'd like to pass it a value. This should return a node. Okay, we also have the remove method. So obviously we'd like to go and search something and remove it. Remember what was the return type of remove before?
Boolean.
Good. Boolean. What other methods did we define before?
Is empty.
We defined is empty. Okay, so this is going to be Boolean. And size.
Mm-hmm.
We defined size. Was it important or not?
Yes, it's important for the loop to start from the middle or the end.
Yeah. Okay. And the attributes, we need the size variable. What else?
Node.
Node what?
Head and tail.
Good. Head. Okay. And we can also define the tail. Okay, there you go. So that's your entire W linked list class. Now let's see how this is going to work. So this is my API. We have these methods defined in there. Okay. This is really easy. How do you define this one? DLL.
And size is equal to 0. Node head is equal to tail is equal to null.
Very good. Okay. So size in the beginning should be 0. And by default, the head and tail should be null, should be empty. The beginning, of course, if the list is empty, head and tail are also empty. Okay. We can already talk about these empty method. That's very easy to implement, and size, but let's do this in later. So let's look at the insert method now. How do we insert something? Okay. Any questions so far?
No, thank you so much.
So if I want to draw my node class, I'm going to use this illustration. Okay, so again, it's just a symbol. I'm just using this shape. So this one would be pointing to node previous. Okay, this one, we are already using the same shape, node next. And this one is going to contain the integer value that we're storing in this node. So I'll continue using the same shape. Okay, for the single linked list, what did the shape look like? Okay, this was the next, and this was integer x. Okay, we use this thing for single linked list. This one we're going to use for the double linked list. Okay, right away, is this going to take more memory or less memory?
More memory.
It will take more.
It will take more memory, right? Okay, again, I'm jumping back to the previous slide. So here, why are we studying double linked list? Why?
To search easier.
Okay, we want faster search, we want faster insert, and we want faster remove. Compared to what? When you say faster?
Single link.
Single linked list. Okay, so we're saying that this is going to work this way. If we implement it that way, we're going to have a faster search, insert, and remove method. Okay, but now we didn't say what was the cost. So
Yes.
can you think
Memory.
about it now? Memory. Okay, so we're going to take more memory, but eventually your program should run faster. So think carefully now. We're talking about space or memory and time. So for a customer, which is more important, space or time?
I think
Time.
Time.
Don't you think both of them are important? Time
Yeah.
and time, space costs money, right?
Right.
Yeah, and money is of course important to your client.
Mm.
Time is also important. We want things to finish early, but at the same time, we want to have a reasonable amount of cost for running the program. If I cannot give it the entire memory in the world, I'm not expected to buy it or ask the customer to buy lots of RAM in his computer for one program to work. Okay, cannot say that. So at the end, it's going to be a trade-off. You have to work with the space and the time to come up with a better solution. Okay, so far so good. Let's try to understand how the double linked list is going to work. So I'm going to start with insert now. Okay, if you remember when we were talking about single linked list, we said that there's 3 scenarios. Either we insert in the beginning, okay, either we insert in the beginning, or insert in the middle, or insert at the end. Okay, so let's think about this. And what if the list is already empty? Okay, so if it is empty, that's very easy to work with. We have the head. Okay, there's the tail. Head and tail. Both of them are in the beginning. What's the value of head and tail in the beginning?
Null.
Okay, good. Both of them are null. So all I have to do is, if my list is already empty, okay, what do I have to do? To check if the list is empty. If head equals to null, this means what? My list is empty. Okay, list is empty. So what do we have to do?
Head
It's easy.
equal new null, a new node equal.
We're going to create a new node. We can say that node. Let's go with temp, or you want to go with n? Okay, let's use n for new node. N node n equals to new node. Okay, and we're going to go and put the value over here. Okay, so which node is it? This one or this one?
It's the second one.
The first one?
Second one. Okay, now we're working with double linked list.
Yes.
We're working with double linked list. So it's going to create a new node like this.
We'll have a head and a tail.
Okay, here's my new node. All right. Now what do we have to do? We have to point the head and the tail, because right now the head and tail are both empty. So I have to say that head.
Stop next.
Okay. No, head equals to n. Yani head points to n.
Yep.
What about the tail? Tail also points to n. Both of them point to the same node. All right. We didn't say anything about this one, this value and this value. What should be these values?
If we're not using a default constructor, we should make them to n.prev is equal to null and n.next is equal to null.
Okay, good. Yes. So by default, the constructor should have taken care of it when you said that. Okay. But just for the sake of clarity, I'm going to say n.next equals to null and n.prev equals to null. All right. Should we do something about the size?
Plus.
Yeah, size plus plus. Okay, so naturally size would become 1. But do you have to say size plus plus, or I can simply say size equals 1?
I think plus because like each time you add a new one.
No, but this code is going to work only when
Yeah, only for the first one.
head
So,
equals null. So it
what's
doesn't
more
matter.
optimal? Actually, I don't know.
Yeah, it's okay. So you can use this one or that one. That's fine.
Are they both like the same? I don't know, like time. Like, is it the same optimization for both? Like,
Yeah, it will be just one additional operation, but we'll talk about it next week. How do we count these operations?
okay.
Okay, so far so good. Any questions? Okay, good. Now let's look at a situation when we have to insert something in the beginning. This means that the list should already be there. Okay, so let's go with this beginning. So there's a head, and there are some nodes which are connected. Okay. How do I know how many nodes are connected?
So
From the size?
From the size. Okay. Remember, so here we've said this thing. This should be null, and this should be null. Okay. We've said this thing over here. So this means that if you keep extending the list, okay, this thing should be null, and this thing should be null. So tail.next would be null, and head.priv would be null. Okay, so now we're going to try to understand how do we insert something in the beginning. Okay, so I'm going to create a new node. So we're going to have a new node like this one. Okay, I'd like to insert this in the beginning. So what should we do?
We can declare the next as the temp, which is the head, and make the previous is equal to null.
Okay, we like to attach this in the beginning over here. Okay, so this means that this node should connect to this one. Okay.
With the temp.
So yeah, this is my n. So we're gonna say n dot next equals to this node. What's the name of this node?
Equals to head.
This is the head.
And then head is equal to.
Right. How about this one? What should happen to this one? If this is going to go in the beginning,
we
okay.
can see
Oh, yeah.
head equal to
Make it null.
Null.
So it should be null. So we have to say n dot previous equals to null. Okay. So this process is called preparation. So it's saying node n equals new node, and of course we're going to give it the x value. So we're preparing this node. We first created the node and we prepare its links. Once the links are ready, we're going to go and play with the list. Okay, so once this is ready, now we're going to go play with the list. We're going to say connect this one. It should not be null anymore. So currently this is head. This will go back over here. Okay, so I'm going to say head dot previous equals to n. Head dot previous, this is the previous, equals to n. So we go connect this. All right. Everything fine? Something is missing?
we need to move the head to the end.
Sorry?
We need to assign the head to end.
Good. So we have to update the head. So we have to say head equals to n. Okay. Is this clear?
Yes.
Let me redraw this because, okay, just to make things easier for you. Okay, so here's my new node. Okay, now we're saying n.next equals to head. So this points over here. Okay, this is my first pointer. n.priv equals null, so this becomes null. Then we say head.previous equals null. So head.previous is this one. Head.previous becomes n. So this is 3. Obviously, this goes away. And then the fourth one is head equals n. So we cancel this one, and this becomes over here. Okay, so now you can see this thing, the list is starting from the head, and we've attached the node in the beginning of this list. Right. What should be the if condition? How do I know that the node needs to be inserted in the beginning?
N.x maybe
If head equals null.
no. If n.x smaller than head.x.
Yeah, it depends on where you would like to insert it.
Yes.
Okay, So whatever is the if condition, you decided to do that, okay? However you decide to do that, it needs to go. But we need to be sure about one thing, which is the head, okay, the node that needs to be replaced, okay? So head will be in the beginning.
Head does not equal to null.
No, head is not null. That will be this case. Okay, if the head is null, this means you're inserting in the beginning, but the list was empty.
Oh.
So here, head is the beginning, and head cannot be null.
Head.priv equals null.
Of course, head.priv is always null. Head.priv is always null.
Should we use the size?
Okay, yeah, so you're trying to determine how do we decide to insert this in the beginning. So it depends on the application. Let's say we go by the value. Okay, we had 1, 2, 3, we'd like to insert 1. 1 is smaller than 2, so 1 goes before 2. Okay, so in that case, my condition would be something like
n.x smaller.
Dot x is smaller than head.x. Okay, so this is an example. It could be any other reason that you'd like to insert in the beginning. Okay, any questions about this? Is this clear?
Yes.
Okay.
Should we increase the size for the code? Size.
Very good. Of course, we had to say size. Like, can I say size equals 1, or do I have to say size plus plus?
Plus.
Yeah, we're not sure about the size. We cannot say size equals 1. So it's better to say size plus plus.
Doctor, if it was not like 1, 2, 3, it is like a string and another string and then another string. Can we just use size to determine the if statement?
Yeah, for example, let's say you're trying to maintain the position. Okay, let's say your application says go and insert at position 2, or position 0, or position 1, whatever. So in that case, yeah, you can use a size variable. Okay, so we're done with the beginning case. Let's look at the middle case, how this is going to work. Okay, how to insert something in the middle. Right. So we have some lists. We don't know how many elements are there before. Okay, and there are some elements after. So these two are connected together. Okay, and let's say this is 8 and this is 10. And we would like to insert a new node in between these two. Okay, so let's say there was a temp variable. Okay, a temp variable, which we use to determine where to insert some new node. So let's say here's my new node that contains 9, and I would like to insert it between these two nodes that contain 8 and 10. Okay, so how to do this?
We have to point the arrow of the 8 to the 9, and then point the arrow to the 10.
Doctor, I think we should make the 9 point to 10 before pointing the 8 to 9, so
Okay,
that nothing is deleted.
But now you have to be very careful with this. Okay, if I do this first and then remove, obviously this removes that. Okay, now you cannot reach 10 because you've overwritten this. You cannot reach 10. 10 is lost. So you need to be really careful. The order of statements is very important. Okay, so rule of thumb, first prepare the node. So I'm going to say, just like what I did before, node n equals a new node. Okay, obviously go for the x value. And then I'm going to say n dot previous. Okay, n dot previous equals to this node. What's the name of this node? We're referring it using temp. Okay, so n dot previous is temp. Right, let's do this one. Okay, how to write this? N dot next equals to
temp dot next.
Do you have a name for this node?
Temp.
Yes, temp dot next.
Okay, so I did not specify a variable for this one, but I can use temp. So I can say temp dot next. Okay, why? Because temp dot next is already pointing to 10. So basically, it simply copies the key. Okay, copies the address of 10 on n dot next. So this connects it. Okay, so now we're done with this. Once we're done with this, now you can go ahead and change these pointers. So let me use it in color. Okay, this is 1, 2, 3. So this is 1, 2, 3. Now what we need to do is we need to connect this one. This dot previous goes over here. Okay, so how can I say this?
Temp.
Do you have a name for this one?
Temp dot next.
Yeah.
Can we say temp dot next dot previous?
Good. I can say temp dot next dot previous. I can say that. I can also use n. I can say, because it's already connected now, I can say n dot next dot previous. So whichever you like to use. Let's go with the temp. So we're saying temp dot next. Okay, this is temp. Temp dot next is this node. Dot previous equals to n. Okay, so now this is gone. Connects over here. Right. We'll do this one now. This one connects over here.
Yeah.
Right. How to do this one?
Temp dot next equal n.
So temp dot next
Equals n.
equals to n. Temp dot next equals n. There you go. Okay. So these 5 lines of code that ensure that you insert something in the middle.
Doctor, I'm having trouble connecting, so can you explain it a bit more? Re-explain it.
Yes. So again, very quickly, we like to insert a new node between 2 pre-existing nodes. So let's say our algorithm decides that this is a temp and the new node needs to be inserted after it. Okay. So what we do is we create a new node. We say n.previous equals to temp, n.next equals to temp.next. Okay, once you prepared your node, then what we do is we update the links in the list. Okay, it's important to be very careful over here because you can make mistakes. So we're going to say temp.next is this node, the one that contains 10. Dot previous equals to n. So this connects this link. So 10.previous connects to this one. And then we say temp.next. So this is temp.next equals to n. So it goes and points over here. So this has updated both of these links, and the old ones are gone now. So if you want to redraw this list, okay, it will kind of look like this. So we still have temp over here. Okay, this is now pointing to a node that contains n, which is now pointing to a node that contains 10, and 10.prev is 9, 9.prev is the node that contains 8. Of course, we have something over here. So far, so good?
Yes.
Yes.
Doctor,
Yeah.
in the sample code for the W linked list, you said as a comment we always insert in the beginning. Why is that?
For the single linked list, you mean?
The W linked list.
Okay, depends on your application. For efficiency purposes, inserting in the beginning or inserting at the end is the fastest. Okay? But what if your application requires that you insert somewhere in the middle? Okay, maybe your data is pre-sorted. You would like to maintain the sorted order. So in that case, the beginning and the end will not work. Okay, it needs to go somewhere in the middle. Where exactly, we do not know. We have to go and search. Okay, that may take a long time. At the end, you decide where to insert. So let's say temp is pointing to where you like to insert the data, the new data. So after this, we go and insert this node.
Oh, okay.
Okay, let's look at insert at the end. Okay, so imagine there is already some data over here. Okay, I'm just going to put some dummy values. And this one is empty. How do we insert at the end?
The tail instead of empty.
Okay, remember, we're always maintaining a tail variable. So tail would always be pointing to the last node. And what we want to do is we want to insert something at the end. So I assume this should be easier.
Yes.
Okay, but let's try to do this. So we're going to create a new node, just like before. Just put the value in there. Okay. Now, if we know that this node is to be inserted at the end, then n.next must be
no.
It must be null. Okay. What else?
The previous.
Good. N.previous must be equal to tail.
Yes.
Okay. And what else do we have to do?
Have to change the tail.
You have to change the tail, and you also have to maintain this one. Let's start doing this thing. So node n equals to new node. Okay, we're going to say n.next equals to null. Again, this should have been handled at the constructor level, but just for the sake of learning. And n.previous must be equal to tail. Okay, so we'll be pointing to the tail. Now what we do, okay, we need to update this link. We need to do this. So how do we do that?
N.previous or tail.next.
Now tail.next equals to n. Okay, tail.next equals to n. And the last thing, we have to move the tail. It cannot be this anymore because you've already inserted a new node. This should become tail. So
n.tail.
Tail equals to n.
Oh, okay.
Also size plus plus.
And of course size plus plus.
Even if I wrote, if I write tail equal tail dot next, it will be right.
That should be right. Very good. Yes. Okay. So for the sake of understanding, let's say temp was over here. Okay, and if temp.next is equal to null, that should be this scenario.
Doctor?
Yep.
For the insert in the middle,
Yes.
the temp should point in the head, right? Until
No, we're not sure. Basically, the idea is that we're looking for the right place to insert. So let's say we would like to insert after 8. So in this case, temp is pointing to the node, okay, with or after which the new node would be inserted.
Yeah, doctor, I mean, should the temp should point to the head and move the temp until we reach the number we want.
Yes, of course. Okay, so we've talked about the middle case, and now we've discussed the end case. Okay, so yeah, I try to break it down into 4 different cases. Okay, the empty case, the beginning case, middle case, the end case, so things will be easier for you. But of course, when you write your own program, you can make it even more optimal, because you can see that lots of code over here is repeated. Okay, you can see this thing every time we're creating a new node, the blue code is always repeated. Look over here. It's almost always the same, with a few exceptions. So what is changing is the red code, okay, or the black code. That is different. So this means that eventually when we go and look at our code, it's going to look more efficient or nicer. Let's have a look at it. Okay, so we go to link structures, in source, here's your double link list. Let me quickly show you the node class. So this is the node class. So you can notice I've defined the priv, next, and the x value. And we've defined 2 constructors, the default constructor and the other one that takes x value. Okay, so it's very identical to what you've seen before. Oops. Okay, and here's your double linked list class. Can you all see it, or is it too small?
We can see.
Okay, good. So here's a double linked list, and we've defined the head, tail, and the size. So this was our API. Okay, about half an hour ago we talked about this. So this is the API. Okay, so your node class and the double linked list class. So we define the size, head, and the tail. And with that, we're going to have some other methods, like the default constructor. The default constructor makes everything either null or 0. So size is 0, head and tail is null. Okay, we have the isEmpty method. It simply returns if the size is 0. Or you can also see if the head equal null. In that case, we also return 0. Okay, this is the toString method. That's very easy to look at. There's a search method. We'll talk about this thing in a second now. And here's the insert method. Okay, so node n equals new node. First we prepared the node. Okay, if is empty means the list is empty. Which case is this? Remember the 4 cases that we studied here?
First one.
Yeah, which case is it? So if the list is empty, this is the first case, case 1. So what we do is we create the new node. Okay, so you're saying head equals to tail equals to n, size plus plus, and return. So this is exactly what's happening over here. My code seems to be a bit more efficient compared to what we wrote over here. Okay. All right. So in this particular code, we're always inserting at the beginning. So this is the beginning case. So end.previous equals null. So this is this one. Okay, beginning case. So end.previous equals null. End.next would be equal to head. And we're going to say head.previous equals n. So you can see this. End.next equals to head. Head.previous equals to n. And then, of course, we are going to change the new head. So head would become n, size plus plus, and we return. In this code, we're not inserting in the middle. We're not inserting at the end. Okay, it's always inserting in the beginning. What's the difference between inserting at the beginning or inserting at the end? Do you think the code is identical or not?
I think it's similar.
Yes, Doctor, it should be very close to each other.
Yeah, it should be almost identical. The only difference is For the ending case, we're dealing with the tail. For the beginning case, we're dealing with the head. Okay? So here we're saying the new node dot previous would be equal to null. But there we'll be saying new node and dot next would be null. Here, after you've inserted, the new node becomes the head. There, after you've inserted, the new node becomes the tail. Okay? So the code is very similar. If you're looking at the time, how long is it going to take to insert this node either in the beginning or at the end? Okay, it will be the exact same time. So the slowest one would be inserting something in the middle. Okay, why is it slowest? Because
you need to define for connection.
You need to search.
Okay, number one, you have to search. That's the main reason it's taking longer. Okay, imagine you have a very long list. We're talking about 1 million elements in there. So you have to go and check every one of them, search the most appropriate, the place that where you have to insert the node, where you decided to insert the node, and then you're going to go and insert these four nodes, or update these 4 links. Okay, so for a computer, this one is going to take 4 lines of code, basically. Okay, we're updating 4 links. Here we're updating only 3 links. In the beginning, we're updating only 3 links. So for a computer, okay, 3 links and 4 links almost means nothing. A computer can do, let's say, 1 billion operations in 1 second. So what's 3 or 4? Doesn't make a difference. It's almost nothing, almost 0 time. Okay, so this was our double list.
Sir,
Yes.
I have a question, a small question for the middle one.
Sure.
The condition to work of the middle one should be temp.next is not bigger than x.
Okay, again, this is just an example. So we can say the same if temp dot x, okay, is bigger than n dot x. Okay, so yeah, you can come up with this. You can have while loop on top of this, and whenever you find this value, then you stop, break the while loop, something of this sort. Okay, let's look at the search method now. So imagine we have some list which has a head. Okay, there's nodes there. And the last thing would be the tail. Okay, we're looking for some node. So let's say this is 1, 2, 3, and 4, let's say. So we're searching for 3. Okay, if somebody says search 3. So naturally this returns a node. Okay, how do we search for a node that contains 3? So this method is going to be identical to what we've studied before. Okay, single linked list. So we're going to have node. Oops. So node temp. Where should we start? From the head or from the tail?
Tail.
It doesn't matter.
Okay, let's do both.
Same thing.
Let's do both. It doesn't matter basically. So node temp equals head. Okay. So while temp is not equal to null, we're going to check if temp.x equals to x. Okay, this is x. So if you found it, what should we do? We stop immediately and we return the node. No. Temp. Okay. If not, then we move forward. We say temp equals to, how do we move forward?
Temp.next.
Temp.next. Okay. So imagine you started from here. Here's the temp. Okay, start from here. Temp is at the head. We're searching for 3. So we come over here. Temp is not null. Of course, it's not. If temp.x, yeah, 1 equal 3, no. So we say temp equals temp.next. So temp goes over here. Okay, again, temp is not equal to null. 2 is not equal to 3. So go temp equals temp.next. Okay, I'm going to come back again. We found it. So we're going to return this node. Remember, we're not returning 3. We're returning the node that contains 3. But what if this was also 3? Which one would be returned?
First one.
The first one.
The first one. Okay. So imagine we were searching for 5. 5 is not there. What's going to happen?
Error.
No.
No, we can't return some. Return false.
We go all the way until the end. Okay. The last time temp equals temp.next, temp will become null because this one is null. So the loop would stop, and we should return null. Okay. Returning null means that we did not find what we're looking for.
Yeah, well, if we didn't return null, then it's an error.
Yeah, of course.
Yeah.
Okay. Now, let's try to do
Doctor.
the other way around. What if we go this way? Would that make a difference? Let's see. Node, search integer x.
Doctor, if we make the loop go while temp.next does not equal to null, it won't check the last node, right?
No, it will. So it goes like this. Okay, let's say last time it was at 4. Okay, so it's not 4. We say temp equals temp.next. Temp equals temp.next. Temp will become null. Next time you come over here, it's null, so it will stop.
No, I mean temp.next. If we use temp.next instead of temp, does not equal to null.
Yeah, true. If you put temp.next, it will not go to the last node. Yes.
Okay, thank you.
Okay, so let's see this one. So now temp equals to till. Okay, and then I'm going to use the same loop. While temp is not equal to null. Okay, so if temp.x equals to x, return temp. Okay, and how do you go this way? Temp equals temp.priv. Okay, so we go backwards, we go this way. And everything else is the same. Return null. So does it matter if I start from the right to left or left to right?
If it's a big list, then yes, because like if you want to search something that, like for example, a big number, then you'd start from the tail, and then if you want something small, you'd start from the head.
Good, but this will work only if the data is sorted. What if the data is not sorted? What if it is?
Yeah, if it's not sorted, then it doesn't matter.
Yeah, so if the data is not sorted, then it doesn't really matter. Okay, here's another interesting fact. What if your list kind of looks like this? You have 1, 2, 3, 4, 5, 6, okay, 7, 8, and 1 million. Okay? So imagine we would like to do the search. We know that this is already sorted. Okay, we know that it's already sorted. So somebody says, hey, please search 1 million. Where should we start? Right to left or left to right?
Well,
right
to left.
I'm searching 1 million. So looking at 1 million, you assume that that's a very large number. So let's try to search from right to left. Maybe I'm going to get it faster. And indeed, you get it faster. Okay.
Yes.
What if somebody says, hey, search 8?
Oh, then you'd start from the left, because 1 million is...
If you already know that 1 million is the last thing, so yeah, in your head you're thinking, hey, maybe 8 should appear on the left side of the list. Yeah?
Yeah.
So if you start from left to right, you're going to do 8 searches. If you still start from right to left, it's going to be only 2 searches. See? So that's a problem. It's unpredictable. We're not exactly sure, okay, where the value would be. So what we do is we look at the worst case scenario. So, okay, in the worst case scenario, it could be the last element. Okay? So it doesn't matter if I go from right to left or left to right. It may take the same amount of time, approximately. So that's the reason searching in a double linked list or single linked list is not optimal.
Yes,
Whatever you say.
Whatever I say, okay. All right, so let's go with remove now. Okay. So okay, remove could be a bit tricky because when you try to remove something from the list, okay, we have to be very careful with the links again.
Oh, not to remove.
If you mess up something, you're going to mess up the entire list. So you have to be really, really careful. Now, just like insert, we'll have the same 4 cases. We're going to have empty list,
Okay.
beginning,
middle,
and middle.
Yes.
Okay. So let's look at empty. What if the list is empty? So in this case, that will be easier to check. Okay, we can simply say if head is null. Okay, what should we do? If head is null, should we go and remove something?
No, just return null.
Very good, just return. Remember, this method is returning a Boolean.
Yes.
And false.
Oh, false, yeah.
Okay, so if head equals to null, return false. Do you also have to check the tail, or there's no need?
I think there's no need.
There's no need.
If the head is null, the tail is null.
Yeah, if head is null, tail must already be null. So we already know this. So return false. That's very simple. This is your empty case. Okay, should we do something about the size?
No.
Because it's already not.
It's already 0. Okay, it doesn't have to change. Okay, let's look at the beginning. The beginning case. So we have head. Okay, we have something here. And I don't care how long the list is. Simply want to go and remove this node, the one in the beginning. Okay, so let's say we searched using temp, and now we've arrived at the node that contains a value that needs to be removed. So here's my
Doctor, if it's in the beginning, do we need to search?
Let's say remove X. Okay, so we search temp. Okay, which points to the node that needs to be removed. Removable node. Okay, so in this case, what do we do? Now, this is straightforward. Removal is easy. Okay, all I have to do is I have to say head equals head.next. Okay, head equals head.next. So again, you have to be really careful about this. If you've said that, you lose this node. This is gone. You cannot access it anymore. So you need to be very careful before you work with remove. Okay, something else needs to change.
Yes, head.next need to be brief.
Previous
Not to be null.
Okay, Let's do this one first. Okay, this is 1, this is 2. Okay, why should I do this? I need to say this node dot previous equals null.
Yes.
So
Now
head
it
dot
will
next
be head
update.
now.
head dot previous equal
So
null.
we gotta remove the head. So head dot previous equals to null. Okay. Now what about this one?
Also, Doctor, size minus. We need to decrease the size.
How about this one? Do you have to do something about this?
No, it's already removed, Doctor.
No, it's not.
Yeah, it's still point.
When we said head,
temp dot next equal null.
This one is still pointing over here. But the thing is, once a method finishes, okay, we expect this to go away. Okay, so if you want, you can leave it like this and expect the Java to go and clean up the garbage because this node is not accessible anymore. So you don't have to write code for this anymore. Okay, now the only thing left is size. Should we say size equals 1 or something else?
Minus.
Minus.
Okay, size minus. There you go. That's going to take care of it. Do we have to do something about the tail?
No.
No.
Are you sure?
Yes.
Yes.
Okay, think about this case.
Yeah, if it's head and then node then tail.
Okay, so you need to be careful. Okay, moving on.
In this case,
Let's look at ending. Okay, so we have some list that contains many nodes, and these are the 2 nodes at the end. Of course, this here is a tail. Okay, what should we do? So assume the node that we want to remove is temp, which happens to be tail.
yes.
So
Should we
we'll do the same,
reassign the
Doctor.
tail?
If temp equals to tail. Okay, so what do we do?
Tail.
Change the tail?
Yes.
Yeah.
Tail dot equal temp dot previous.
Tail equals tails dot previous. Okay,
Yes.
tail goes over here. That's number 1.
And then we just do tail.
And then what?
Tail
dot next equal null.
next equals to null.
Good, this one. Okay, we don't want to reach to this node. So tail dot next equals to null. Okay, dot next equals to null.
Doctor,
Yes.
if we say tail.previous.next is equal to null, is this the same?
No, you have already changed the tail.
From the beginning, before we do this.
Oh, yes, that should be fine then. In that case, you can say tail.previous.next equals. Yeah, you can say that. Okay, what else?
The size, Doctor, we need to decrease it.
Size minus. You have to change the tail or that's it? We're done.
No, we're done.
We're done. Okay, so just like the beginning case, it's only 3 lines of code. So 1, 2, and of course the size. Okay, this is for the end. Hey, what about the middle? That's tricky. Okay, so imagine this is temp. Okay, we'd like to remove the temp. Go to something over here, something over here. Hey, first of all, how do you know that temp is in the middle?
Searching.
If condition, if
both next and the previous are not null.
Okay, temp dot previous is not equal to null, and temp dot next is not equal to null. Okay, this means this is the middle case. So this is the situation. What should we do?
But this could be anywhere in the middle, right? Like it's not exactly in the middle.
Yeah, it can be anywhere in the middle.
Yeah, we can see Dr. temp.previous.next.
So do you want to get rid of this node?
Yes. We can say temp previous dot next equal temp dot next.
Okay, good point. So we just have the two lines of code, and that's it. Let's try to do the first line of code. So what is this one?
Temp dot previous.
Temp
dot next.
Dot previous.
Dot next.
Temp dot previous is this node.
Mhm.
Dot next equals to
Temp dot next.
this one is temp dot next. Okay, the other line of code, this one.
Temp dot next.
Temp dot next
Dot previous.
dot previous equals to temp dot previous. Of course, size minus minus, and then you're done. Is this clear to everybody or not?
Yes.
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 Okay, if you think this is difficult, what you can do is you can put some other labels. You can put, let's say, A and B, okay? And then you can work like this. You can say A dot next equals to B, and B dot previous equals to A. Okay, of course you can define A equals to temp dot previous, and B equals to temp dot next. Okay, there's more lines of code, but essentially it's the same thing.
Doctor, I have a question about the size. I know you said we will discuss it next week, but
No, it's okay. We can discuss now. It's okay.
You said that the difference between size plus plus or size minus minus and size equal 1 is one extra operation.
Yes, yes.
So the size plus plus will need to go check the current size, then add 1, while the size equal 1 will just reassign the size to 1 regardless of the current size.
Yeah. Okay. Look at these three statements. So we're saying size plus 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 size, and size equals 1. So it depends on how your compiler, okay, compiles this and how your computer executes this code. How many operations would be done? Remember last time we talked about the cycle?
Yes.
Okay. So fetch, decode, run, save. This is our cycle. So it depends on the architecture of the computer. How many operations, or how long is it going to take to process this? So is this equal to 1 operation? Is this equal to 1 operation? Is this equal to 1 operation? It depends on factors. For example, where is the memory? Is this happening only in the CU? Is it happening only in the arithmetic logic unit of your CPU? Okay, is it going into the register? Is it going into the cache memory, and so on? So generally, this is supposed to be faster compared to this one, because naturally both of these would be in the register, okay, which is the local memory inside the CPU. This could be in the RAM. Okay, imagine there's an array of at position 1 equals to 1. So you have to go to the memory to fetch this value or store this value. So don't worry about it, but we'll talk about it next week, inshallah.
Okay, thank you very much.
Doctor, can you go to the previous slide, please?
Sure.
Between at the red lines, number 1 and 2, if we switch it, would it make it run?
It doesn't matter. You can try it.
Matter.
You can try it. You can say temp.next.prev equals temp.prev. No, it's fine. You can switch the lines.
It's fine. Okay. Thank you.
So if you don't have any questions about this, let's look at the code now. So here's the remove method. Okay, so again, if it is empty, simply return false. Okay, and here's a temp, and we're looking for a node that's going to contain the value. So this is a little bit of searching. So we try to search for a value in the list. If it is not there, we simply return false. I don't have to write this code. I can simply call the search method. But just for the sake of explanation, I put this code in there. Now here's the three scenarios. If you want, what you want to delete is the head. Okay, so we simply say head equals head.next, and head.previous equals no. So we saw this thing over here. This was the beginning case. So head equals head.next, and head.previous equals no. Okay, same thing. Same goes with the tail. So if tail equals to temp, so tail equals tail.priv, and tail.next equals to no. So with this thing over here, tail equals tail.priv, tail.next equals to no. And then this is the middle case, just two lines, the ones that we saw a minute ago. Okay, so the order does not matter, you can change it. And of course, at the end of all of this, size minus minus, and return true. So there you go. This is your entire W linked list. There was a method about search. Did we see the search method? I think we did. Yeah, so here's a search method if you're looking for a node that contains the value x. So you can go from right to left, you can go from left to right. It's up to you. So this is going from left to right. We saw this thing, it does not give you any benefit if you go from left to right or right to left. In both cases, the runtime would be the same.